Jilla. Kyungtae did his bachelor's and PhD at KAIST in South Korea, working on optical frequency phones and also quantum gas experiments of various kinds. He's been a postdoc in Jilla since 2021, and he's now a senior research associate working on some really cool stuff. Optical lattice clocks. This is, the most precise measurements that you can make of time. So please welcome Kyungtae.
Hello. Does it work? Thank you for the kind introduction. Thank you for having me here. It's a great pleasure. I'm trying to share some excitements about physics in application of optical lattice clocks happening in Juni's group in Jilla, Colorado Boulder. So it's basically two parts. One is I try to convey the concept of optical lattice clocks, and later part I'm probably going to a little bit deep on the research and try to be as exploratory as possible, but please feel free to interrupt me anytime. This is my first colloquium, so I'm a bit nervous. So physical frequency standard. So I'm from the clock research, so I like to talk about the standards. So when you try to define the time, what we do is, I think in my point of view, is two things. We want something physically ticking, like it doesn't have to be like pendulum. It can be like electronic signal, whatever. It doesn't matter. It's something like consistently ticking, and we should be able to make many of them. And once you make many of like these oscillating things, and imagine they are like you compare different oscillators, and they're ticking at the same rates. And then you can start to think about maybe, oh, we can define time out of this. Maybe you can start to convince yourself, oh, this might work for talking about time. So turns out oscillating electromagnetic wave or electronic signals can be served as a good ticking stuff. And we are especially good at measuring this zero crossing of the voltages in your electronic devices. If you count how many zero crossings are happened, then you can start to think about time. And you need to make them like consistent. And turns out it's easier to use atoms instead of like sculpting like artifacts like some optical cavities or something else. Why is that so? In my point of view, because this quantum mechanics kind of works. So we have standard model that's well established. We have periodic table. They look kind of complicated. But if you twist a little bit, it's not that many. So we have some like identical stuffs. So quantum mechanics permits only like specific configurations of the matters, of course at usual energy scale. And they're really identical. How identical? You can even form like so-called bosons and condensates, which I guess Brian's working on. And so you cannot even like label the particle with like 1, 2, 3. And James Thomson sometimes quoted it as like quantum certainty instead of uncertainty. If you have strontium atom, if you have hydrogen atom, the one I have is the same. So can you make a ticking signal out of these atoms? That's like a idea of atomic clock, my point of view. So how do we get the mountain time? Please check out this time.gov website. You can get a nice website that officially supported by NIST. So each national lab in the world, they have their own free-running atomic clock. They're continuously running ticking signal. And they're like about like 400 oscillators. This is called like EAL. It's like French names, Echelle, atomic something. I don't actually know. And then they are like drifting away. They're slightly drifting from each other. But then every month, every national lab actually send this ticking signal to one place, and they compare each other. And then they calibrate this ticking signal against the so-called like primary standards like Cesium fountain clocks and so on. They're like 25 frequency standards, and this is called TAI, or International Atomic Time. You can also search like circular T on the internet, then you can see what kind of atomic clocks are contributing to this game. And then you have to, because the earlier definition of the time was based on the astronomical observation, so you need to like phase match with your Earth rotation. So sometimes they put some leap seconds to just like artificially increase 1 second in the midnight or something. And I think they started not doing this, but yeah, that's what happened. And then that's called UTC. And then if you subtract 7 hours, like numerical value, then you can get the mountain time, which is like the clock over here. So the thing I'm trying to say is the old timekeeping, the signal on your phone can be actually traced to some ticking signal, which is referenced to the atoms, which is kind of, I find it cool. And if you go to NIST Boulder, you can actually find this blinking signal that counts many zero crossing and flashes one light if they think it's passed by 1 second. So that's like the official 1 second that you're looking at. So the current definition of the second is based on the cesium atoms hyperfine splitting. I guess Christian is working on cesium atoms too. Maybe somebody else is too. And that's about like 10 to the 10 hertz, like 10 gigahertz. And in the near future, scientists are thinking of redefine the seconds based on the optical transitions, which would have like 500 terahertz or something. In the future, we want to increase the base frequency further and further because of this obvious reason. If you have a higher frequency, you can easily resolve the how much time passed. So it's kind of release the stress for the time maintainers, and you can do the more precise timing comparisons. So it's good for everybody.
Wait, so what's the altitude at which this is defined?
Altitude.
This is wherever the clock happens to be, right?
Yeah, that's there.
Okay.
If you're sitting here,
yeah,
you have a 1 second. If you have a cesium, if you're here, you have 1 second. But when you compare, because you send the light towards a higher altitude, it gets shifted. So you have to.
So if we're defining mountain time in Jilla, which is at a higher altitude than let's say where this Gaithersburg is there an account made of these differences?
I believe there will be difference. Then, yeah, because this is so it depends on how precise you want to get. So of course, although I said this, if you use the internet because of the protocol, it's not precise. But if you actually want to get the really nice timing signal from the list, you have to consider those altitude difference. You have to like if you set up like satellites and so on, you have to calibrate the rates. Yeah, because of the gravitational redshift. Yeah, conceptually, I want to highlight the difference between time and frequency with some analogy with different stuff. So I can call it like time as x, then the frequency is like x time derivative. So you can think of this as a position, but while frequency is like something like velocity. So what we do is like keeping the velocity and hoping the position to be the same over time and over. And in the optical clock world, this time is kind of like laser or radio frequency. It's continuously ticking over time. And we can calibrate the velocity of this thing with the atoms. And these are, you can think of it as a resonant induced dipole. So it's inherently, fundamentally, it's a frequency reference, not the phase reference, because atom's phase will follow your laser phase. So optical atomic clock, for me, it's like a simple spectroscopy experiment. You just like do the spectroscopy very well. So I phrase it as like counting your laser frequency resonant to your atomic transitions. So you send the laser to the atoms and you ask how much frequency is off from your resonance. And you just keep feeding back this information to your laser. Then your laser become the ruler for the time. And there's an interesting device called frequency comb that allows us to count the optical frequency. I'll describe it more later. So these three elements are basically the fundamental elements for optical atomic clocks. So speaking of lasers, so science in the laser is basically fighting against the thermal noise. So current state-of-the-art laser is based on cryogenic crystalline silicon fabric cavity, just like a mirror facing each other. And this length, I'll say the L here, is that defines the frequency of the resonant mode in this cavity. And if I express the stability in terms of like fractional units, delta F divided by F, or corresponds to delta L divided by L, is about 4 times 10 to minus 17. If I quote like proton radius, this is like 10 to minus 15 meter or femtometer. So it's actually moving much less than the size of the proton over time, within like 1,000 seconds or so. And why we use this cryogenic silicon material, this is because of the thermal expansion coefficients close to 0 around like cryogenic temperature, and it's crystalline, so it's very rigid. I'm going to explain why you need a rigid material. So this is the noise budget. Y-axis kind of like noise, and this is like different iteration of the material. This is like a fully silicon cavity case. You see this red is the dominant source. This is nothing but a coating on your mirror. So to make a mirror, you need to like interleave different like materials like brackets. Here, Arizona University is like one of the best places you can do this. Is Garrett here? I guess new faculty Garrett is one of the experts. I think, and then somehow, surprisingly, this 10 micrometer thick mirror coating is the dominant source of this cavity. They are like, because of the thermal temperature, the crystal structure is slightly moving. We call it like Brownian motion. That's the dominant source. And we've been making this with the amorphous material, which has low mechanical Q factor. So low mechanical Q factor means you're more strongly connected to the environment. So this thermal fluctuation can be easily propagated into your motion of your lattices. Your software you have, like, is easier to move for a given temperature. So you need like more rigid or high Q material, it turns out. So I think Gerard Cole and Marcus Aspermeyer, and in collaboration with June, they pioneered the crystalline mirror coating based on the semiconductor material. Because they are crystalline material, we expect them to have higher mechanical Q factor, and then it was like promising approach. And it turns out there's another interesting problem. If you're interested, I can talk more about it. But yeah, I believe future is in the crystalline coating. So you have three silicon cavities in the lab. That's like a performance of one of the cavity. Unfortunately, I forgot to put the X label here, but it's like 6 years of period, and it's drifted by like 5 kilohertz over those periods, or correspond to like 2.5 picometers. It's like amazing, and they're so predictable. And this cavity is made of single crystalline. So I think people thought, oh, they won't drift away, but then somehow it drifts away. And we have in the world, there are like 3 or 4 operating silicon cavities. Somehow they are drifting in a similar speed, and we don't know why. So if you have some idea, please let us know. We are super interested about this drift. I hope it stops. So yeah, even with this amazing laser, the laser is actually still the dominant source to mark. And so we are privileged to this laser, and then we transfer this stability of the optical cavity to many different kinds of lasers. And now it supports like 10 experiments, including GILA. GILA and NIST are kind of in the physically separate place. We are like 4 kilometers away. And but we have like telecom link to NIST. We're actually sending this light to NIST, and they're also enjoying this amazing stability of the silicon cavity. So as I said, we have like multiple cavities, so we can beat 2 lasers. We can like combine 2 lasers in the beam splitter, and you can measure the bit nodes. And this is what you see in the lab. I wanted to get you a feeling of the silicon cavity. They're offset by like some like hertz. And then another postdoc is match the frequency, and then you see the phase drifts between two different cavities. They're like slowly moving away from each other. You can have a feeling that you want to correct this signal like every seconds ish time, and that's what we do. Like that, we use the atoms to correct this phase excursion every seconds. That's like how optical atomic clocks working in our lab. So frequency comp, it's a bit of appreciation actually. So every time I think about this, it's kind of interesting. So how to count an EM wave, like zero crossing? And we wanted to count the zero crossing, but how do we count 500 terahertz signal? That turns out to be non-trivial for a while, I guess. I'm probably too young to talk about this, but it's been a while to a human to figure out how to do this. And if you can think about, like, for measuring the oscillating electric field, one can think of antenna. It measures electric field, but it cannot go 1 terahertz. You can use a photodiode, but it just measures the intensity. There's no information to phase. So I guess to me, the problem is like conducting electrons are too slow. Turns out if you use like extreme nonlinear optics, you can actually make this rainbow frequency spikes, Dirac combs, and then you can actually breach the RF frequency to the optical frequency. So you can actually use the existing amazing RF infrastructure to the optical domain. And thanks to the birth of this frequency comp technology around late 90s, we can start to think about precision measurement of the optical frequencies. And this leads to a Nobel Prize, and JILA is one of the places that frequency comb is had a birth. And it's actually colored rainbow. It's actually pretty. It's kind of nice. Yeah. So this is like the last part, and then this is the last part of the fundamental three elements, and this is mostly the part, the thing I'm going to talk about the rest of the talk. So called optical lattice clock. It's proposed by Professor Hidetoshi Katori around 2002, and first, optical lattices is a very efficient and clean way to quantize motional energy for Doppler-free spectroscopy. It's a lot of words. Doppler-free means if you have atoms flying around, it has velocities. And if you shoot the laser, it'll get the recoil too. So they change like velocities and so on, so there'll be a broadening of your spectroscopic signal. But then if you confine the atoms in some conservative trap, if you quantize enough so that the motional energies are discrete, like it's like a harmonic oscillator, then you can start to avoid these kind of like problems. You can avoid kicking the atoms because of the lasers. For that, technically, we need a very tight confinement. And optical lattice is nothing but a standing wave formed by two counterpropagating laser. And this is, if you think about this period, this is like a lambda over 2. That's like a finest period, the most, the fastest frequency, spatial frequency you can get out of the laser. So you can very tightly confine them. And then I say clean because that's by far the highest frequency, spatial frequency you can get. So you don't have like a higher, faster corrugation of your optical potential. So you can actually expect very clean potential for the atoms. So that actually allows us to do a very homogeneous, build a very homogeneous environment to probe the atoms. And there's another idea called magic wavelength. Because we probe different state of the atoms, they can have a different polarizability. Here, the y-axis is a polarizability of the two different states, and x-axis the wavelength. And because of this rich structure of the atoms, sometimes they have the same polarizability at the certain wavelength. Then you don't need to worry about the frequency difference caused by frequency inhomogeneity caused by the optical trap. They have like their experience with exactly the same trap depth, so you can do the very precise spectroscopy. So by the way, if you're working on the atomic physics world, you can check the marianasafronova.com. She's our collaborator. She recently, this year, she launched the online polarizability plot available for everyone. So it's very nice for atomic physicists. And I guess I've heard of the Paul's earlier work. I believe that's like one of the first observation of quantized motion in neutral atom. Is that?
I believe so, yeah.
Yeah.
But it's part of the furniture now.
So this plot actually shows up in the older textbook. So I was happy to visit Arizona for. Yeah, so I was like, yeah, it's an amazing plot. So you need to choose the right atoms for optical clocks. So we want this is a energy level structure of the strontium atoms that we like, and I'll say there are like two kind of requirements. One, we need two symmetric orbitals so that you have like you need to make the atoms to be insensitive to the environmental perturbations. We just want to measure the energy gap between two orbitals, not like environmental fluctuations, electric field, B field. So in technical term, we want like total angular momentum of the orbital to be zero for both states. And we also want to very narrow line width. Narrow line width means it doesn't decay fast. So if you think about decaying, atoms are decaying, as you know. If you excite the atoms, they emit the photon again. But if this decaying time is too fast, you just don't have time to define the frequency. You just cannot like probe your atoms as long as you want. So you need like very long living atoms. So this is often, so for that, we often use so-called forbidden transitions. Forbidden means by the symmetry of the orbitals, it's hard to drive. But there's a little chasm in this nature. So we use that like a little defect in the nature to drive the atoms. For strontium atoms, we have two valence electrons. So we love to have like a closed J equals 0 states like this, 3p naught and 1s naught. These are the electron orbital that you often see in the chemistry. And then this is because there are two electrons, you can actually make a symmetric orbital with the p parity. And we use these two levels in this line as our clock transitions. So if you are deep into the quantum mechanics, you might seen perihelium and orthohelium. These are basically have the same symmetry as those terminologies. Okay, so we need to we kind of like choose the atoms, and then we need to bridge the atoms with the lasers. So for that, we need to use two very classical spectroscopy methods. One is Rabi spectroscopy. Following the Rabi, we just shine the laser continuously to the atoms, and then you measure the excitation fraction. Then if you change the laser frequency for some range, you will see this peak, and then this ripples are coming from the square wave of your input signal. And what we do is basically parking our laser to this side of the fringe. So that if my frequency goes up, then excitation fraction goes up. So then, the frequency is too high, so we need to bring it down. So you bring it down, and so on. So we can also do the RAMD, so-called RAMD spectroscopy. It's kind of like a Mach-Zehnder interferometry. So you prepare the ground state atoms, and you pulse the atoms with so that it's been the equal superposition between excited state and ground state. Then you wait for a while. Then the phase difference between excited state and the ground state will evolve against the laser. And depending on this phase excursion with respect to the laser or microwave, you have different consequences after all. And then if you change the detuning, you can see this sinusoidal oscillations. I will come back to this methods again later. But these are two fundamental ways of comparing laser and atoms to correct our laser frequencies based on the atoms. So so for probing the atoms, we use like laser cooling and trapping technologies, and I don't think I need to explain too much about it. You can. So if you go to our lab, if you put your iPhone on our chamber, you can see this strontium atoms in actions. So in the vacuum chamber, we flash the laser light like this, and then you can see these strontium atoms are glowing in the middle of the vacuum chamber, and we load these cold atoms in the lattices, and we shine the clock laser and we read out the excitation fraction. That's like how experiment goes. And you can also feel this like an experimental cycle. Then you can relate this period to the laser frequency excursion that I show you. This is like a period of feedback we're doing. So our main job is understanding the perturbation to these atoms and minimize it. So if we are holding the atoms in this optical lattices, and so this lattice causes lattice light shift or Stark effect. We need to understand this kind of thing. So, and there's a B field fluctuates. Earth generates B field, and magnets nearby fluctuate. So we need to understand these effects. Sorry. And because we load many atoms in the optical lattice, so they collide each other. So it's actually essential to understand many-body physics of this system. Of course, it's the number one enemy is black body radiation. So because we are holding the atoms in the vacuum chamber, this is like a 300K more or less. They emit the infrared radiations. And these infrared radiations are not magic for the atoms, so they shift the energy level of the clock states. So we need to understand those effects. So how do we use it? So we believe these are sensors for the fundamental physics. Of course, we can make a better time standard. And one application I like is you can support the dark matter search. So if you compare two different optical clocks or two different stuff, you can actually talk about the dark matter, ultralight dark matter. So some theories propose that ultralight dark matter's matter wave field will perturb the fine structure constant alpha. If you think about hydrogen, the bound energy is proportional to alpha square. That's because the bound energy is like half mc square alpha square. It's a c alpha is like velocity of electron. And so the bound energy of the strontium is like alpha square more or less. But if you think about optical cavity, the distance between the atoms are Bohr radius more or less, and they're proportional to alpha. So there's an alpha to the 1. So we have alpha square for the bounded electrons. We have alpha for the cavity. So there's like differential power. And if you have alpha difference, if somehow unknown dark matter changes this alpha, maybe you'll be able to see on this frequency difference. That's like an idea, and you can find like more sensitive atoms and more sensitive transitions. And that's like a nice application of the optical clocks. And the other amazing thing is we can think about leveling too, like geodesy. So 1 centimeter height difference gives you 10 to minus 18 frequency shift. Your clock on 1 centimeter above ticks slightly faster, very small amount. But this is we have good resolution, so we actually reach this level. So I'm going to talk about this later a little bit more. And although there are like amazing advances, we think it hasn't reached its fundamental limits dictated by lifetime of the orbital. Well, I roughly like off the shelf back on the envelope calculation, like 100 seconds. If you divide the line by some amount, maybe you could reach like 10 to minus 20 or sub-millimeter relativistic frequency change. But we only reached like just below 1 e minus 18 so far. So in our lab, we are trying to push the performance of the optical lattice clock. What is the best design? What is limiting us? That's like our main research goal. So in our lab, surrounded by this laser, we have many experiments. The first experiment is the experiment I'm working on is just simple 1D optical lattice clock that pushes the best precision accuracy. And we also have like 3D optical lattice clock that kind of like use a clock as a tool for probing quantum many-body physics. And one of the fundamental source of noise in optical lattice clock is quantum projection noise. I will explain later. And a way to get around is using the so-called spin squeezing. And you can also think about entanglement between the atoms. And June is trying to actually show that spin squeezing is boosting the performance of the state-of-the-art optical clock. And as I mentioned, the mirror is under still the dominant noise source. We are investigating the crystal mirror with another silicon cavity as well. And there's a new excitements from the nuclear physics side. We started to excite the isomeric nuclear states. If I have time, maybe I can talk about it a little more, but feel free to ask me questions later. I'm probably not going to talk about this. Yeah, so I'm going to describe the experiment I'm working on. So we call it like strontium 1 because maybe it's 1D or it's first generation. So the question we are trying to address is how far we can push the precision and accuracy. So accuracy means you know where you are exactly in absolute number. Precision is how stable you are, how small is your noise. So it can be inaccurate, also precise, something like that. But they usually goes both together. And June had a very old experiment, and we rebuilt around 2020. It's actually before I joined, and they incorporate lessons they learned from the previous generations. For example, it's good to use camera so that you can use like inhomogeneity of the system or understand this inhomogeneity like magnetic field gradient, density gradients, and so on. And it's good to use a shallow optical lattice because although we use a far detuned laser, the lattice laser is still scattering the photon to the atoms. Then once you scatter photon to your atoms, then this photon extract the information from the atoms, so atoms are decoherent. So it's good to use less laser power, as always. And it's hard to get around from the fundamental interaction strength, so we decided to use very large trap volume. Technically, our cavity wave size is 260 micrometer, which is kind of large compared to usual wave size of the optical lattices. That's why we need this in vacuum build-up cavities for building a lattice. And in this in vacuum build-up cavity also give you a low pass filtering of the special disorders too, and also frequency. So we've been working hard, and then we finally characterized all the systematic effects last year. And this is like basically the table. It looks like, yeah, it kind of looks boring maybe, but then it's like a scoreboard for the clocks. But to me, it looks like an omnibus of atomic physics. Every row gives you, you have to explore different physics like Stark shifts, Zeeman shifts in the detail, and how to measure those effects, how to model those things. So I'm going to walk you a little bit about those elements. And this had been a record accuracy until a few months ago. It's beaten by another clock that I'll also describe later. It's actually from the list. So yeah. So as I described, we wanted to use a shallow optical lattice, but we wanted to orient our cavity vertically so that lattice can be tilted by this gravitational force. So if I picturize that potential, it looks like this tilted lattices. And this idea has been proposed around 2005. And why we want to tilt the lattices? Because if you have just flat lattices, atoms can turn around because of the overlap between different lattice sites, the wave function overlap between the lattice sites. Their atoms are too light so that the momentum uncertainty is pretty large, so you can actually tunnel around the lattice. That's actually why people use optical lattice to study the quantum antibody system like Hobart system. But this is actually bad for optical lattices because if the atom moves, then it means Doppler shift. So we want to avoid that, and that's like spontaneous processes. It just diffuse away. So we don't want that. So that's why we tilt the lattice with the gravity. If you tilt it, because this tunneling is coherent processes, if your energy levels are off, then if the atom tunnels to the other lattice sites, but then energy is not has to be conserved, so it has to come back because there's no way to dissipate the energy because of that. So that actually lifts the energy degeneracy between different lattice sites. So, so if you actually shine the clock laser, then you see these multiple peaks that correspond to a site, one side to one site, or one side to the other side transitions. Like for example, here center black line is we call carrier transition, and these other spikes are basically as you add one more MGH, you can also kick the atoms from one side to the other sides. So we call it like resolved tunneling sideband regime, as this allows us to do Doppler-free spectroscopy even at the shallow depth. Yeah, I used to read the paper from Pierre Meister. I'm not sure if he's here. He actually gave a nice insight in the decay rate of this various dark states back in the days, like 2001, even before this. Still, he's from Arizona, so just brought it here. Yeah, so with this new machine, we improved the coherence time of the strontium atoms quite a lot. So this is our cloud image. This is the atoms in the optical lattices. We took it from the camera. And as we scan the laser frequency, you can see this nice resonance with the up to like 3.1 Rabi spectroscopy time, so that you see this narrow line width. And then basically what we do is controlling our laser to be sitting here, as I described. But this is talking about atom and laser coherence. But we think the atomic coherence time is much longer, but we are limited by the laser coherence time. So how do we quantify the coherence time of the atoms? It's simply comparing the two regions of the cloud. So because of the small frequency difference between two regions, mostly from the magnetic field gradient, we have small frequency differences. And I think this is what I brought from the previous slides. This is from the Ramsey spectroscopy. We have like sinusoidal shape. If you have a frequency differences between two regions, P1 and P2, it means you have a distance between in the x-axis. And then even though you lose the coherence from the laser, the distance between these 2 points are the same. So if you plot the correlation between P1 and P2 and you repeat this experiment multiple times, you can see these ellipse patterns. And this visibility of the ellipse will tell you there are still the atomic coherences there. We just lost the laser coherence. So in that way, we can prove the atomic coherence time much further than the laser coherence time. At the time, like 2020, we got like about 0.5 minute of coherence time, and recently we found we have a better number than this, and I'm going to talk about it later. And because we kind of reject the laser noise, we so often call it a common mode rejection of this laser noise. And this is actually a very useful technique to measure the frequency difference between two regions. Sometimes you're not interested in the laser frequency. Sometimes you're just interested in the frequency difference between two atomic ensembles. So there's another fun many-body physics. Before that, I want to warm up a little bit. So there's one of the dominant noise source of the optical lattice clock is quantum projection noise. So quantum kind of means like digitizations. And measuring the excitation fraction of the two-level system is basically a coin tossing problem. You have many, many two-level systems. They're basically coin tossing. And if you combine them together, you have a fluctuation because of this stochastic trials. They often follow the binomial distribution or Gaussian distribution. And that scales with 1/√n, just like a normal statistics. And so unfortunately, we cannot load like infinite number of atoms, of course. So that kind of sets the some noise performance we have. So we want many, many atoms to reduce the quantum projection noise. But if you increase the atom number, there's interactions coming in. For making clock, you want to really avoid interactions between the atoms because they're like spontaneous. They just dephase each other. They shift their frequencies. That's the reason why we choose fermions, which does not interact each other through the strong S-wave channel because of the symmetry of the statistics. So we chose a fermions, but still there's a P-wave interactions although it's like very small compared to conventional like ultra-cold atom systems, but it's still very strong in the clock world. It's like 10 to minus 17 or 16, but we are looking for 10 to minus 19, so this is like bad. And they scales with the atom number. So there's like a competition between we want more atoms and we want less atoms. So there's a trade-off on this like systematic effect and the noise, statistical noise perspective. And we also find the dephasing rate, decoherence rate of the atoms also scales with the atoms. And atom numbers, of course, it's hard to control. Well, nowadays people start to make a Twitter experiments. They can have different control. That's a seems different story, but right now for this kind of ensemble experiment, it's pretty challenging to control the atom number very precisely. But then, thanks to Anna Maria group, we found a very interesting case where many-body physics can actually help precision of the clock, our clock. That's been published in this paper. So we love to call it as engineering interactions. So in the optical lattice, we have lattices like this, and we load the atoms in this way. And then we shine the clock laser, and those two lasers must have different frequencies. We cannot like trap the atoms and excite the atoms with the same frequency. There's a period mismatch between clock and lattices. So each lattice sites pick up different laser phase, phi, let's say phi. And then each lattice sites, I can assign phi, 2 phi, 3 phi, and 4 phi. And if you think about the excited states for each pancake, each site, you can write it in this way. G plus e to the I phi times m, this excited index, times e. And as I described before, because of the Tifania-Stock wave function spread, there's a crosstalk between two different pancakes. But these phis are different for each lattice size. So each different pancakes start to talk to each other in a S-wave manner because they are now distinguishable. They are not like identical fermion anymore. So they are strongly interact with S-wave. Strong, but the overlap interval is small, so it's not as big. But luckily, their sign is kind of opposite, so we can actually find a cancellation of off-site S-wave and the on-site P-wave. So y-axis here is a frequency shift per atoms, and x-axis is the lattice depth. So if you change the lattice depth or the extension of the wave function, we were able to find like almost zero density shift at certain lattice depths. And we love to call as a magic lattice depth, where we kind of like remove the effect of the collisions. That's actually very good news for us because we can increase atom number without worrying too much about the systematic effect or something. So it's a good case where we gain with both accuracy and the precision. And you can actually see that on the camera very apparently. So y-axis here is a fractional frequency difference between different atoms, and x-axis is the basically height. It's like a coordinate. I showed it as a horizontal way, just like this image. Mm-hmm. Oh, this is a full range. It's like 3 millimeter. I forgot to put the scale bar. Yeah, this is 3 millimeter. And you can see out of the magic depth, we have like a more or less Gaussian shape frequency shift because of this cloud shape. The density is like higher right here. But if you are close to near magic depth, it's gonna flatten out. This is actually very exciting for us. And this lead us to have estimate the differential frequency in a very precise manner. So we were curious about like gravitational redshift here because we are clock, why not? So what you can do is, as I described, if you compare two different regions of the cloud, you can remove the laser noise, which is dominant vector. So if you just compare these two regions, we can get this pretty nice frequency resolution. So y-axis here is the uncertainty when your frequency difference between two regions. The time here is basically how many times you repeat. So as time goes, you just repeat many times. It just goes to square root tau or like square root of number of repetitions, and we get like this amazing instability. And remember, 1 millimeter corresponds to 10 to minus 19 time dilations. So can we actually see the falling photons from this lattice clock? So we try to correct the systematic gradients. For example, like a magnetic field gradient generates second order Zeeman shift, and we also had to remove the density shift that I described. There's still residual effect. After that, we measure this frequency gradient, residual frequency gradient over like a week. Then we got this number, minus more or less 1, 10 to the minus 19, which is like what we basically expected from the local G measurement. So we're happy about this number. And at a similar time, Shimon Kolkowitz's lab, at the time it was in Wisconsin, they also observed the 1 centimeter scale redshift with a similar technique. So yeah, so there have been various redshift measurements starting from like Pon-Repka's experiment there where they use a nuclear source, Metzbau spectroscopy source for 22-meter power in Harvard. And there's another experiment in Tokyo. They measure the gravitational redshift. It's very apparent because it's much higher from this tower. And there was another optical clock experiment in this. They just literally lift the optical table by 30 centimeters. They saw this frequency shift. And now we are reaching like 1 millimeter, 1 centimeter. And we're hoping to reduce that length scale further and further. Maybe we can reach the 1 wave function size later. So yeah, so and then as I described, it's like an omnibus. So I'm going to talk about other systematic effect too. So I said there's a residual lattice light shift. So it's a question about overlapping between atomic distribution and the lattice light. And interestingly, at the very precise level, B field from the lattice became important actually. So that has been there was a puzzle about this sign of this B field effect. There's a mismatch between experiment and theory, even at the sign of the polarizability coefficient that has been luckily resolved recently. And the B field I meant is if you have a standing wave electric field by at the node of the lattice, your electric field changes fast. There you have a maximum B field. It's very tiny amount, but turns out that's very important for 10 to the minus 17 level. That made a measure wavelength not perfect. And we tried hard modeling this, and we kind of reduced the uncertainty down to like 4 minus 19 level. And during the time, we found a very interesting observation, which I like to share. So if you go to shallow lattice depth, we actually expect this wave function extension, but we don't actually see these wave functions. But we can actually indirectly gauge this effect by observing the Rabi frequency, how the coupling strength between laser and atoms. So if you calculate the Rabi frequency of the atoms with this extended wave function, you need to compute this integral. You have to multiply your density with the e to the I kz, the phase factor of the spatial wave vector. And then this wave function size is now exceeding the wavelength of the clock laser. So you can expect like an average effect. So indeed, if I change the lattice depth and I change the size of the wave functions, and if I go from like 120, let's say 21 units of lattice depth to 13, then we were able to see this big change of the Rabi flopping frequency. This means because of this extended wave function, they kind of cancel the later phase like in a kind of coherent manner. This kind of like tells us, oh, this extended wave function actually is there, and then we're still dreaming about can we actually measure the redshift across these single wave functions. So number one enemy was like black body radiation from the vacuum chamber for optical lattice clock. It's nothing but a broadband AC Stark shift. So we need to understand both response of the atoms, which is called atomic polarizability, and the intensity of the BBR. Turns out the limited knowledge about the polarizability is the main uncertainty of these corrections. And and thus we have to understand atomic dipole moments more precisely. And it's mostly limited by one transitions. So we try to measure the Einstein A coefficient or decay rate, which is more or less telling you how dissipative is this level, which means is how easy to polarize, or it just tells you the polarizability. So we go there, we actually measure for a year about how about this A coefficients, and we step further. We're looking at the literature, and turns out there are like many observations made for the strontium atoms. So you can measure the DC polarizability of the strontium at certain states, and you can people also measure the some so-called tune-out polarizability. Yes, tune-out frequency, all kinds of different quantities and different A coefficients. But these are all can be calculated by the standard formula in the atomic physics. So we're curious, like, can we actually use all this information to constrain the uncertainty of the unknown polarizability we had? And then turns out people have been thinking about this problem for a while, especially in Germany. So we learned from them. So we made a like statistical modeling, and then we like did some uncertainty propagation and so on. And then we were able to reduce the BBR shift uncertainty by constraining those uncertainty of the dipole moments. And this is still the dominant factor for strontium atoms because of the very, very long wavelength transitions of the strontium. This is just character of the strontium, unfortunately. Yeah, so this is still unfinished saga. We believe we can improve further. So as you measure different polarizability at different wavelengths, we can constrain more and more about this. So with this characterized strontium clock, we decided to do a clock comparison with the other clocks. As I described earlier, comparison is like heart of the clock network, making a robust clock. And because we're using the laser, and we can just use the telecom infrastructure. And for example, in Europe, they already have an optical fiber network across different nations, so they can compare their clocks. They've been doing this. And we also have a connection to NIST. And this is the clock that beat our systematic uncertainty in this July. We actually collaborate with them. So we send our pristine silicon light to the aluminum ion clock at NIST, and they actually benefits that laser to characterize the systematics, and they also demonstrate one of the best instability of the ion clock with our laser. So there's like growing efforts on the clock comparison at the high precision through the optical fibers now. So we're trying to compare our clock to the NIST clock. They have two different clocks, aluminum ion clock and the ytterbium clock, and we're connected through the fiber again. And then the motivation here is we report the uncertainty budgets, but we haven't shown this is like the uncertainty we have. So for that, we want to have like experimental confirmation of this budgets. So we need to validate our budget. The only way we can do is just comparing different clocks. So and then our clock and the aluminum clock and this are rebuilt. So we kind of want to compare it again. And then now at this time we have an architectural improvement. Everything's locked to a silicon cavity, which wasn't the time. And then earlier this year we finished the campaign, and we reached like 3e-18 fractional uncertainty for this clock comparisons. This is not differential comparison, so the uncertainty is not as impressive as before, but it's actually we believe this is one of the best independent clock comparison so far. And along that line, we also want to contribute to the TAI in the future. As I described, there's an ensemble of primary standards and secondary standards. We actually want to register our clock to those games. And we also want to demonstrate the all optical timescale, which means the ticking signal so far is based on the RF or microwave signal. But in the future, we believe the laser can replace that role. But directly doing this timescale with laser is not trivial, so we are also demonstrate a better way to do this. And then on the left, locally, as a like atomic physics machine, we wanted to understand what's limiting us further and further. So, so we we actually improved the vacuum lifetime of our machine quite a lot, and that actually helps us to increase the coherence time, just because we can use more atoms without losing too much of them. So it turns out, instead of like half a minute of coherence time, we actually have 2 minutes of coherence time. And based on these understanding, we were able to demonstrate like a factor of 2 improved relative instability, meaning you can average down like 2 centimeter relativistic frequency shift in a seconds and so on. This is differential. This is not like a cloud operation. And interestingly, the decoherence rate is strongly dependent on optical lattice depth. That's partially because of the lattice photon scattering and the increased density as you increase the lattice depth. So we wanted to go. So as you see here, it's just y-axis basically a decoherence factor. As you go shallower and shallower, the decoherence rate goes smaller and smaller. You can enjoy longer coherence time, but then at some point it starts to grow like rapidly. That's because again, because of the extended wave function, these interlayer interactions come into play, and that's stopping us going to even shallower depth. So, but then we came up with a cute idea. So we decided to remove one or the other latticite atoms. So step one is like we just prepare the atoms, and then we shine another standing wave on top of this lattice, and it has to have twice the wavelength, so that you stock shift away for one or the other lattice sites. And then if you do the clock laser scan or Rabi spectroscopy on top of this situation, you can get these 2 peaks, which is like the orange here, orange area here correspond to this stock shifted line. The other area is basically an unshifted line. And we can simply blow out these atoms by exciting those atoms to a clock state. And then we can prepare these states. Then once you prepare this, and if you do the scan again, we don't see this peak anymore, meaning we actually prepare the one or the other sites atom configurations. And we do see a continuous decrease of the decoherence rate after we do these processes. So this blue is after we site selects, and this is the same curve as you saw, this like V-shaped one. So we are happy about this results. So, yes, interlayer as yeah. So this part, the taking off part is from the interlayer. So yes, it's only P wave limits. And there's another idea of doing atom interferometry and the optical clock at the same time, meaning we want to measure the gravity, like acceleration, and the laser frequency at the same time. So as I described earlier, we can drive a so-called carrier transition and also the offsite transitions. So if you average these 2 +1 and -1 offsite transitions, you can get the laser frequency. But if you take the difference, you can actually get the MGL, lambda L. Lambda L here is the wavelength of your lattices. So we just keep measuring these 2 different transitions over time. We can actually get two information at the same time. We can track the laser frequency, and also we can also measure the small g from this known coefficients of m and lambda L. Sensitivity is like comparatively very small, very bad actually, because the splitting here is only 1 lattice sites. It's not actually comparable to the atom interferometry yet, but we're excited about this new idea, and we hope we can actually split the wave packet further and further in the future to get more sensitivity. Oscillation here? Yes, so this is actually sensitive to the tilt of the lattices, we believe. And then we don't have at the time we designed this apparatus, we didn't think about this reflection, so we don't have a tilt control on our lattice. So I think what's happening is as the temperature slowly changes over time, the lattice is like slowly tilted. It's actually very challenging. It's like a 10 milliradian kind of precision is required. So we don't think we can do an absolute accurate measurement of the G, but we think it's nice idea to push forwards. And if you have a nice sensitivity, maybe you can try to think about building on new experiments. This idea is like not really new. There's been a push towards the distraction without the clock transitions, just using the Raman transition of the atoms. And here, Chris Panda is also trying to do atomic interferometry with its trapped lattice geometry. And in the future, we're excited about this gravitational redshift measurement. So we are trying to connect the relativity and the quantum mechanics with these precise clock. We are looking for what it can do and so on. So back in the days when the atomic interferometry was like claiming some redshifts, there was a nice discussions about atomic momentum position superposed clocks, and then because of the so this idea here is if you can make a special superposition of the clocks and you excite the atoms, and then later you combine them together, because of this redshift, you can actually tell which path the clock's been through. And that information kind of like couples the external state and the internal state, and they kind of change the Ramsey visibility. And it's kind of like a nice target goal for us to push forward the atom interferometry plus clock ideas. And with collaboration with Anna Maria, we thought about is there any what's the consequence of redshift plus many-body physics? To be honest, in my point of view, that's kind of similar to magnetic field gradient. But the neat thing about this proposal we made is we might be able to like test the relativistic effect by just dressing the mass. So we can like maybe we can control the effective mass of the atoms by applying another laser that dress the ground state with the excited state. Then maybe we can tune the mass defect in a controlled manner. That's like one idea. And because we have a Vanya stock ladder and we have a clock laser, if you think about this problem with two drives, like two drive means carrier transition and one offsite transition, that's actually nicely mapped to the Su-Schrieffer, SSH model, like a classic topological bonded chain experiment idea. And then we figured out there's a topological pumping protocol. We can robustly split out the wave packets. So maybe in the future, we can implement those ideas too. Yeah, those are things we have in mind. And then with that, I'd like to thank you for your attention. This is our PI, Juni. He's always inspiring us, motivating us. This is me as a grad student, Alex, Will, and newly joined Kai. And this is Mariana Sapronova from Delaware. She's done like lots of atomic structure calculation and discussed about the BBR shifts. This is Anjun, and Anna Maria is here. Anjun's one who actually figured out, oh, there must be a density shift cancellation from SNP wave when he was looking at the theory. Yeah. Thank you for your attention.
So, one quick question first. Since the BBR shift seems to be the limiting factor, if you put the setup in a built edge or a old situation, how would that help?
Yeah, that's the way to go.
Okay.
People actually try to pursue that direction. Then we are not pursuing this direction right now because we want to do more sciencey stuff.
Sure. Yeah.
We want to harness the differential comparison further.
Makes sense. So I mean, but that would be one way to overcome the current limit. But the other things like spin squeezing and such will also improve your system, which is the more physics way of improving the sensitivity of it.
But the only mark is we don't actually know about systematic effect of the squeezing. The spin squeezing actually shift the frequency. We don't actually know what's the consequence of spin squeezing.
Right.
And cover out this.
Not in the near future.
Aluminum profitable.
Huh?
Aluminum iron is hydrogen, right? No.
So good thing about the aluminum ion is if you strip out one electron, the binding energy is much higher. So all the transitions are actually further pushed towards UV, so you're less sensitive to the BBR. So that's not actually their big old problem.
Brand new field to me, so once you like get a handle on the current noise to what's driving it, what do you think the next culprit will be for the noise? What comes after what's your current like?
That's the game, right?
What's the next nail in the coffin?
I think it's magnetic field.
Magnetic field noise.
Magnetic field noise. But that's still technical. But magnetic field noise is so if I give you the number, 1 Gaussian field or Earth field gives you 15 Hertz frequency shift. But for the 1 millimeter redshift, we need like a sub-millihertz level. So we need like 100 ppm corrections for that. So
At that point, you can fly off to space.
that'd be great. Or aerial, or you can think of
The price compensation, right, already, so 1 Gauss is 3.
Yeah. With we have to like be more careful. Yeah.
I think that's a bit hard.
Yeah, and then noise is also another. So you can, if you go cryo, maybe it actually solves everything. But then it's hard to use camera, so we are thinking of you need some careful design.
Great talk. Thank you. So I know you mentioned that black body radiation is one of the biggest limitations.
Wow.
So you mentioned how well, I was hoping you could explain what characterizes atomic polarizability. Like what is it?
Okay, so actually, thanks for asking the question. That's like a part I like about. So let's see, where is it? Okay, here. Yeah. So this alpha is a polarizability that you can like read in the basic E&M course. P equals to alpha E. That's alpha more or less. And you can actually calculate it with this formula. It's kind of complicated. There's like frequency dependent term, but there's a coefficient. That's like a dipole moment square. So atomic dipole moments. But in the experiment, what you measure is directly the polarizability at a certain wavelength. But these are all based on the formula. So all the curves are kind of fixed. You have to like scale those amplitude by the A coefficients. We have some data for some of the points here. So we can like you can think of like least square fitting of these amplitudes based on those experimental data. That's how we kind of characterize. Or you can also directly measure the excited state lifetime like this. You excite the atoms, look at the photons, how they decay exponentially. But then it turns out it actually causes there are like lots of systematic errors. For example, atoms are talking to each other, maybe kind of like about it, but it's kind of systematic for us. So we need to be careful about that. And that precision is kind of like percent level, actually. So we actually want better. So that's one methods.
Any other questions? Time for one more question.
Go back to the diagram with the coils, a lattice in the middle.
So, coil.
Back where you had the diagram of the actual like lattice vacuum cavity. And coils and stuff. This one is. Yes.
This one.
What is temperature probe?
That's for the radiation, black body radiation characterization. So we thermalize our calibrated sensor with the radiation from the outside, and we try our best to isolate from the thermal propagation from the arm, and then we believe the sensor is thermalized by the radiation, and by just measuring this temperature, we can actually tell about the intensity of the BBR. That's how we calibrate the intensity part of the PBR, not the polarizability part.
Thank you.